another problem where we need to find state transition matrix and inverse state transition matrix. You know what do you mean by state transition matrix? In state transition matrix, any state vector initial values can be transferred into the final values. If x of t is phi of t is x of 0, which means the x of 0 is the initial state vector, can be transferred into x of t, the final state vector, using the vector matrix phi of t, which is called state transition matrix or STM. Now the system model is given like this: x dot is equal to 0, 1, minus 1, minus 2, and B matrix is 1, 0, u. So for this, find out STM. Then we have formula available, so you can use the formula directly. So your phi of t is Laplace inverse of SA minus A whole inverse. So we know that S is the Laplace variable, A is identity matrix, and I is identity matrix, A is the system matrix which is given. So we can simply substitute there and you can get what will be the SA minus A, and also you can find out the inverse of it. Then inverse of it will have the 4 elements. And these 4 elements I can say phi 1 1, phi 1 2, phi 2 1, phi 2 2. So I have 4 elements and I need to find the inverse Laplace of it. So if you find the inverse Laplace of it, for each element find out inverse Laplace of it. Then you can recollect the formulas of inverse Laplace transform. Some of the important inverse Laplace transform I am listing here. They are very useful when you are finding phi of t or x of t or y of t in a system. So these are a result of your inverse Laplace transforms. Let us say I have a function k by s plus a, it is inverse Laplace transform is going to k into e power minus a. Similarly, if I have k by s plus a power n, then it is k by n minus 1 factorial into t power n minus 1 into e power minus 80. Similarly, if I have k by s power n, then we have k by n minus 1 factorial, we have t n minus 1. So e power term won't come here because of the only s power a. Then if you have k by s plus a into s plus b, then we can write as a k by b minus a into e power minus 80 minus e power minus bt. So these formulas you can remember directly, you can substitute wherever it is coming when you are finding the inverse Laplace transform. Similarly, we can have, if you have k by s into s plus a, where a is equal to 0, when you substitute a is equal to 0 in the previous formula, it results in k by b into 1 minus e power minus bt. Similarly, if you have inverse Laplace transform ks by s plus a into s plus b, numerator I have s, in that case k by b minus a into b into e power minus bt minus a into e power minus 80. So these 6 or 7 formulas very important, especially in state model or state space analysis, where you can directly convert the phi of s into phi of t, or if x of s into x of t, inverse Laplace transform very useful. Now, so individually if you try to find out, you can easily say that your phi 1 1 is going to be e power minus dt plus t e power minus t, and phi 1 2 is going to be t into e power minus dt minus t, and phi 2 1 is if you find the inverse Laplace of it, and you are going to minus t e power minus t. And we can also find out what is phi 2 2. So given the system, we can easily do the partial fraction, and all the cases we need to do partial fractions before applying the Laplace transform. So it results in phi 2 2 is nothing but e power minus t minus e power minus t. Now when you write all these things in a matrix, which is a state transition matrix, what will be the STM? When you write all the things here, your phi of t goes to, the first element is e power minus t plus t into e power minus t, second element is t e power minus t, and third element is minus t e power minus t, and fourth element is e power minus t e power minus t. So this is my STM. Then how to find inverse of STM, inverse state transition matrix? We know that phi of t inverse is nothing but phi of minus t. So wherever t is there, substitute minus, then you will be getting the result very easily. So inverse STM is nothing but phi of minus t, that which is inverse state transition matrix, which results in again 4 elements I have. So e power t minus t e power t, then we have minus t e power t, then we have t e power t, then we have e power t plus t e power t. So this way we can find out STM as well as the inverse STM. Let us look at another problem in state space variables. The problem statement goes like this. So consider the state model given below and find a STM. state transition matrix. B. The solution of the state equation for unit step input. C. Output response for unit step input. The state model is x dot is equal to, we have 0, 1, minus 2, minus 3x plus 0, 1 u. So y is equal to 1, 0 x and x naught, x of 0 is equal to 1, 0 transpose. So this is a state model and also we have initial conditions. So since we have initial conditions, then we need to find the state solution of state equation as well as the output response of the system, how the output response is going to be. Now, so the first part of is state transition matrix, which we know already how to find the state transition matrix. As per the definition, state transition matrix is phi of t is equal to Laplace inverse of Si minus A whole inverse, where S is the Laplace variable and I is the identity matrix, and A matrix we know it is 0, 1, minus 2, minus 3. So when you substitute here, so we will be getting Si minus A and whole inverse, and so then after that we need to find the inverse Laplace transform. Then we have already readily available formulas to find the inverse Laplace transforms, and individually you can find out for phi 1 of s, phi 1 2 of s, phi 2 of s, and phi 2 1 of s and phi 2 of s. For this individually if we find, and we will be getting it as the final results, phi of t as 2 e power minus t minus e power minus 2t and e power minus t and minus e power minus 2t and minus 2 e power minus t plus 2 e power minus 2t, and we have 2 e power minus 2t minus e power minus t. So these are the four elements which we have phi 1 1 of t, phi 1 2 of t, phi 2 1 of t, phi 2 2 of t, which are inverse Laplace transform of those corresponding Laplace equivalents. So this is what STM, that is state transition matrix. So this STM is very useful to find both in solution of the state equation and also the output response of the system. Then the second part of the problem is find the solution of the state equation. So we know the equation for it. Then the x of t we can write it as phi of t x of 0 plus Laplace inverse of phi of s b u of s. And we know the first term is nothing but ZIR, 0 input response. The second term is ZSR, which is 0 state response. So individually find it and finally we add to get the x of t. So we know that we need to find the solution of state equation for unit step input, which means input is available. When input is available and also initial conditions are given. So both ZIR and ZSR will be available in expressing the x of t. Now, so first of all we will find what is ZIR. So ZIR is your phi of t into x of 0. Then what I can do is instead of writing all phi of t here, I will write the phi of t as phi 1 1 of t, phi 1 2 of t, phi 2 1 of t and phi 2 2 of t, and into I have x of 0, which is nothing but 1 0. So we have taken transpose of the given in the problem. So then what will be getting, you know, it is 1 0, so that you will be getting the first column. So your ZIR is nothing but the first column, phi 1 1 of t and phi 1 2 of t, and corresponding terms we can pick up from the phi of t, and that is 2 e power minus 2 minus t, and we have minus e power minus 2t and minus 2 e power minus t and plus 2 e power minus 2t. So this is nothing but my ZIR. Similarly, you can find out ZSR. What is ZSR? Laplace inverse of phi of s b u of s. So what is u of s? It is unit step input. U of s is going to be 1 by s. And phi of s is also available. What is phi of s? Si minus a whole inverse. So phi of s readily available. I can write the phi of s as phi 1 1 of s, phi 1 2 of s, phi 2 1 of s and phi 2 2 of s into I will multiply the B matrix. So what will be the B matrix? B matrix is 0 1. So when it is 0 1, this phi of t B results the second column, which is phi 1 2 of s and phi 2 2 of s, and that will be multiplied with the u of s. U of s is 1 by s. Then in every term we will be getting the denominator on extra term. So then you find out what is inverse Laplace transform of these two terms alone, need not find for all the terms. Then if you find inverse Laplace transform to these two and when you write ZSR, then it is going to be 0.5, minus e power minus t and plus 0.5 e power minus 2t, and the second term is going to be e power minus t minus e power minus 2t. Then when you combined ZIR and ZSR, which results x of t expression, the x of t expression is going to be now again two terms here, because there are two state variables x1 of t and x2 of t, and the first variable is going to be so minus e power minus t, and we have minus 0.5 e power minus 2t plus 0.5, and the second term is going to be e power minus 2t and minus e power minus t. So this is x1 of t, this is x2 of t. Now what is the output response for unit step input? So we know that y of t is nothing but c into x of t and d is 0, and c is nothing but your 1 0. Then you will be getting the first term. What is the first term? x1 of t. Therefore my y of t expression is nothing but x1 of t, and we know the x1 of t which is readily available. So your y of t going to be only x1 of t, so which results in e power minus t minus 0.5 e power minus 2t and minus plus 0.5. This is the output response of the system.